So, just a few important announcements that this is why this week is special. One, it's going to be on Sunday. I will be 24 years old. So if you want to give me something, sure. I like food. I like books. If you, tomorrow on Saturday at the Provo City Library, I have to be there. They actually have like a used book sale, but you can grab as many books as you want for free. So it's this Saturday, December 1st. And also, fortunately, your test is this week instead of next week, because if you want to, you can come to my Welsh choir concert, which is next Friday. I think it's like 6 p.m. or 7 p.m. in the JFSB building. It should be fun. There will be food and stuff like that. And before we move on to anything else, let's just watch a funny video that explains how exams work. Okay. So I have some things I do want to talk about, but I'll take questions first if those are things you would like to go over first. If there are things you'd like to go over first.
Oh yeah.
Yes? Okay. So molecular orbital theory is going to... Yeah, I started. You're late. Let's make it a little bit thinner. So molecular orbital theory is going to be really important. You're going to use it to explain phenomena, and by that I mean why or why not a certain reaction will occur. And you will also use this to demonstrate the presence or lack thereof of aromaticity. And so these are all going to be like pi bond stuff, so it's nothing too bad, but it can be a little bit tricky. So let's just go over it really quick. So let's go over the aromaticity. Aromaticity. So remember, for a compound to be aromatic, it's got to meet the 4 conditions. If it fails any one of these conditions, it will not be aromatic. It'll be non-aromatic or anti. Yes? Yeah, we'll get into that. We'll use MO theory to explain. So an aromatic compound is one, planar, completely flat, even if it's a long species. It has to be conjugated pi system. By this, we specifically mean it's p orbitals or p-like orbitals. So this is with the p-like orbitals, I mean like sp2, sp3, those hybridized orbitals that can potentially participate in the conjugated pi system. The third one is, what is the third one? Cyclic, yeah. The reason why it has to be cyclic, well, we'll get into that in a second. I'll jump into atomic theory to explain that, and of course, Hugel's rule. So in terms of molecular orbital diagram for aromatic compounds, we're always going to build from the bottom up, and we're going to, as we go up in energy, we increase nodes, or places where electrons are not likely to exist. But it's got to follow the pattern 1, 2, 2, 2, 2, and so forth, and then top. So basically, it's got to be the pattern 1, 2, 2, 2, 2, 2, 2, 2, 2, however many it will be, and end up with 1. The reason why that happens is because if we look at the linear compound, let's make this green. These two orbitals on the end, right here and here, are unable, no interaction in linear form. Whereas if we bring them around, we've created that we've created a new type of interaction, which makes it cyclic. So that's why it has to be cyclic. These two, let me say it like this. So beforehand, each carbon has 1, 2, 2, 2, 1 interactions with the carbon next to it. So the ones in the middle have 2 p orbitals surrounding them, but the ones on the end only have 1. But once we cycle them around together, each of the 6 carbons in the chain has 2 p orbitals to access. Does that make sense? And so because of that, we get that special orientation 1, 2, 2, 2, and so forth. Yeah, Kyle? Well, so sp2, so sp3 it's 75% p character, and sp2 is 66% p character. So this is easier to explain with an example. I'll just put it right here. So this is referring to orthogonality, orthogonal, as far as lone electron pairs go. So if we compare, say, this guy, we will do this, and we'll compare it with furan, which is this. So we don't just count that. So for Huckel's rule over here, we don't just simply count the number of pi electrons available. We have to see if these lone electrons will play a part, so to say. But here, when we look at the sp2 hybridization, I'll draw it to the side like this. No, I need that double bond to the nitrogen, or else it won't work. Because this is sp2 hybridized, that lone pair of electrons, it has the trigonal planar species type of geometry. It's orthogonal to the pi conjugated system. So the p orbitals in the ring are like rotating around like this, whereas the nitrogen or electrons are like that. And so because those are orthogonal, these pair of electrons will not contribute to aromaticity. Does that make sense? Yeah. Well, you have to consider. So it is sp2, but it could be a different scenario. Is what I'm saying. So if we take sp3 for example, which is this oxygen right here. So now with the sp3 orbital, it's kind of like this. Well, that's the 1 part s and the 3 parts p. This is not entirely orthogonal to the plane. This is now kind of angled off, so let's do purple. So we've got the pi bonds just kind of sitting around, but the the sp3 orbital, it's kind of off like at an angle. Not at a perfect 90-degree angle or a perfect 0-degree angle, but it's like 30 or 45 or something like that. So 1 pair of these electrons are actually able to ring around the rosy, help us out. Yeah, because what happens with the second pair of electrons is they're just going to become orthogonal to the plane. So yeah, this is tricky. So that's why it's important to know the difference between aromatic, anti-aromatic, and non-aromatic. And let's get into more of a description of that right now. So we all understand why the molecular orbital the orbitals take the 1, 2, 2 position instead of just the 1, 1, 1, just them all stacking on top of each other. And I'll actually write that cyclic, and then planar. The nodes, I mean, the orbitals simply stack on top of each other. Less stacking, completely stacked. And when we compare these orbitals with each other, the linear species with the cyclic species, something special actually happens. So we'll take the pi 2 over, so we have pi 1, pi 2, pi 3, whoops, pi 3, and they all just line up nicely. In the aromatic compound, both of these will kind of average out. Notice I said kind of, into pi 2 and to pi 3, which is this one right here, and they'll take the same shape. So the pi 2 and the pi 3 orbitals, so the pi 3 plus pi 2 over here equals the energies of the pi 3 plus the pi 2 over there. They've got the same number of nodal planes combined. Yeah, that's right. But pi 1 actually, when we put it into an aromatic cyclic compound, it actually way drops in energy. The pi 1 of the cyclic, I'm not sure how much less, but it's a good deal less. And so the reason why aromatic compounds become so stable, whoops, I didn't want to erase it. What color do we like? We like pink. Now let's make that thicker. This whole thing right here is the reason why aromatic compounds become stable. If you walked in late, notice this meme I put on the notes right there. This is one of those things you want to pay attention to. Yes, I have. Okay. What? That's a pot smoker? Oh, whoops. That's the good guy, Greg. Oh, you're right. Okay. So now that we get into this, why the aromatic compounds become more stable, you know, I'll keep red for the these are the things you should really notice kind of thing. Yeah, Kyle? Well, this is the cyclic aromatic conjugated. So by that we specifically mean benzene. And by this we just mean like something linear, non-cyclic. Yeah, so something like a linear straight chain alkene with the bonds rotating. I mean alternating. The cyclic aromatic conjugated compound. Yeah. Well, no. The stabilization comes from the pi 1 because the pi 1 here. The pi 1 over here is a big drop in energy. This is the orbital down there. We get more conjugation from this one. This is a lower energy level than this one. These two, like I wrote right here, pi 3 plus pi 2 plus pi 3 plus pi 2 over there. Yes, well, the sum of the two. So Wesley and Saul, I think. Yeah, right? You have a question?
Oh, yeah. So could you explain why pi 1 drops so much? Is that just
Basically, it's more like it's kind of like a shielding effect where the electrons on top of it bury it underneath. So like if we think about the periodic table where we just climb down and we add on another layer of electrons, that's kind of what it's like. The ones near the nucleus get protected. And Sol? Perfect. Now let's get into non-aromatic versus anti-aromatic. So with anti-aromatic, it's going to fight tooth and nail to become non-aromatic, so to say. Non-aromatic is just like whatever. It's just the meh. So to explain how this works, we have to go back to the MO molecular orbital electron configuration. So remember, we've got the orbitals increasing in energy. We've got pi 1. Let's do 4 layers. No, I need an automatic one. Pi 1. Yes, this is for anti-aromatic. Pi 4, pi, whoops, that's a 4. And then just here's the pi stars. I won't bother to label them because those are pretty easy. So the aromatic compounds, all electron orbitals below anti-bonding, this line right here, are filled with anti-aromatic. Some electron orbitals are partially filled. And when we're talking about anti-aromatic, we're going back to the original 4 rules of what makes it aromatic in the first place. So we do need to still consider what those are. Yeah, Kyle, what's your question? Yeah. The general rule. This will be a helpful hint, but whoops. Does anyone like, what color do you guys like? Let's do, I like this color. Anti-aromatic compounds will generally follow the 4n rule. So it's the 4n plus 2 without the plus 2. So the classic example of the anti-aromatic is the that's not, well, pretend like it's an octagon. So we see like, okay, well, we could fill pi 1, pi 2, pi 3, and we go, okay, pi 4. Wait, what's wrong with that? Yeah. See, this right here explains why it's aromatic. Well, because according to the Pauli exclusion principle, so Pauli exclusion principle, it means each orbital must get 1 electron first. So if I have 5 orbitals, I go 1, 1, 1, 1. Each gets half filled. If they're all the same energy level, they each get filled with 1 electron first, and then if we have more, then we can fill them up.
So I guess how did you know the 2 slots there?
For this one right here, so this is the configuration. We pretend like it's aromatic first. So we pretend it has the
cross diagram, each spot is a pi bond.
No, they're 2 pi bonds of the same energy. 2 pi orbitals. Right, because they're the same energy. So I have to go one here, and if I had a couple more, like say I deprotonated this and say this had like 9 carbons on it, 9 nonagon, and we had that pi conjugated system plus 2 lone pairs of electrons. Aha! Now we have those 2 electrons available. So that meets the potential for it to be aromatic. So that's exactly what defines anti-aromatic. These 2 electrons are unpaired and high in energy. So it's going to work against being aromatic. Yeah. So it's just like I said right here. The sp3 orbital and the sp3 orbital, just with the combined with the normal p orbital, they're similar enough in shape that they could overlap. But the sp3, remember when it's like tetrahedral, it's like a pyramid. So like here's the plane of electrons floating around. Here's the sp3 orbital. It's not completely orthogonal. If it's completely orthogonal, no interaction. But since it's like say 30 degrees off, it can come in and everyone's happy. So you can think of it as they're clapping their hands together. Yeah, Kyle?
So how do you know how many electrons to count?
So you always count. So let's make a note of that down here. Oh wow, I'm running out of room. Are these notes good enough?
Yeah.
Okay. Counting electrons. Yeah, I'm gonna phantom record myself later on. What's nice about this is it's like partially shaded in, and as you watch the video, it'll like highlight it in. So it's pretty cool. So counting electrons for 4n plus 2. So we always count pi electrons. Why do we count them? Because they're sweet. Think Pac-Man or turkey or whatever. You may count, or you might count sp3, or we'll say lone pair electrons if they are non-orthogonal to the plane. To the plane of the ring. Right, because one of them, so once we go back up here and look at it again, once these two associate with the two pi bonds within the ring, the other electron pair will become orthogonal. Yeah, exactly. So that's basically the hardest. That's basically the hardest counting there is. Everything else is like willy-nilly. So let's see. Have we covered that well enough?
So whenever you have 2 lone pairs, you only need to count one.
Basically, yeah. Only one of them.
You're counting the ones that are conjugated.
Yeah. Count the ones that are conjugating. And so we've gone over anti-aromatic. Remember this special 4n rule. That'll probably help you out a lot. Non-aromatic. Basically, the only criteria for that is, well, one, it's non-cyclic. So like a linear alkene species. Another case would be either it's non-cyclic or it's non-planar. So basically, if we look at our rules again, it'll disobey one of these three conditions. It might still follow Huppel's rule, but remember we've got to follow all four. So non-aromatic is typically non-cyclic, non-planar, and or non-conjugated. And the only way to really explain that is if you have a three-dimensional model of the molecule. Like you saw with the octatetraene, where it was kind of like the not completely flat, you actually had to look at that molecule first to determine, oh, it's non-aromatic. In its flat form, it's aromatic. In its normal form, it's non-aromatic. Okay, so we've gone over that pretty well. Now, how do we use it? Let's go back to purple. Now, you might be asking, how do we use aromaticity in a reaction? Does someone ask me this question? Well, thank you for asking. This is how we're going to do it. So aromaticity is yet another stabilizing factor that can increase the pKa or lower the pKa in several different ways. So on your modeling assignment, you actually saw a really great example of this. This is probably a hard problem, but oh well. Whoops. We'll take the hydrogen. Oh, use the. Oh boy. Take the hydrogen. What happens with this system? This beforehand was non-aromatic. Now it goes to being aromatic because, oh geez, look, we got extra pair of electrons that we can use to fill that orbital, the 1, 2, 2, 2 pattern. So this is aromatic, and then we have cyclopentane, of course. And so, because we go from non-aromatic to aromatic, that drives the reaction forward. Does that make sense? So it might be a very subtle thing that you do have to keep into account. Yeah. So if we draw it like this, this will help explain why. When it starts conjugating with the other pi bonds or with the other p orbitals in the system, it will become flat. This conjugation leads to subjugation, leads to planarity. Nope. Hyperconjugation can make it planar if it becomes aromatic. And so there is a very specific problem on problem set 10, I think. I want to go over it right now because this is a very, oh, yes, what did I say about it? Red. I think it's number 4. I said those words. I said them, but I lied them. Goodbye, Dr. Seuss. Why not? Okay, let's go back to purple. So we're going to use this to explain why concerted mechanisms do or do not occur. And so by concerted, remember that's happening in one step. And the classic example of that is Diels-Alder. Diels-Alder. And I think the problem, as it states, it's like this is not exactly this is not an exact replica of the problem, but it's close enough. So we're going to take this cyclopentadiene and combine it with here. I know it has fluorines on it. Well, that'll give you clues to where to find this problem. So we're going to propose. We're going to say, like, okay, it's going to take the 5-membered ring and they're going to squish together to form this nice little square. So carbons 1, 2, 3, and 4 become carbons 1, 2, 3, and 4 over here. With, of course, your 4 fluorine atoms. Now, as with all reactions, we still want to identify the nucleophile, which is this guy in this case, and the electrophile. What's the big clue that this is the electrophile? Well, it's got 4 fluorines attached. 4 fluorines are pulling away the electron density from the pi bond. So these carbons right here will become partially positive. In Diels-Alder, I know I had to look this up because I don't remember, but you might want to write this down. The diene is the nucleophile, and the ene, just the 2 carbon, like ethylene, is the electrophile. Good thing I wrote that up there. So we're gonna say, like, well, why not? Why is this not an aromatic? Well, why is it? Oh, went back to pink. No, that's purple. So why is this not a concerted reaction? And when we look at concerted mechanisms, we typically look at pi bonds. So we've got to analyze the HOMO and the LUMO of our nucleophile and our electrophile. So nucleophile, we're going to look at the HOMO, and the electrophile, we're going to look at the LUMO. That's right, isn't it? So in either case, let's draw so we have here 4 nice pi orbitals. Well, not quite. This will be pi 2 antibonding, pi 1 antibonding. So pi 1 will just be the straight wee, where they're all in sync with each other. The next one is this guy. Where one of them is out of sync. The third one, 2 are out of sync with each other, so it's like this and this, this and this, and then the pi 4, or I mean pi 1 star, they're all alternating. This diagram, it will, oh, that's not shaded in. That's, ooh, there we go. Like that. 1, 2, 3. So here's our, So right here.
Just as a note, the recording kind of screwed up, but it's up, down, down. That's how it goes.
Here on our pi 2, we have our HOMO. So I'll redraw that down here where we have and then we'll look at our electrophile, which will just be right here, and it will just have a pi and a pi star. That one's pretty easy because we only have 2 configurations, one where they're both in phase and one where they're both out of phase. So with because it's the number of nodal planes as we increase. So this has 1 nodal plane. Yeah, you could do that. It's the same thing. This, or you're meaning like, oh, no. Meaning like this? Like that? No, I don't think that's up, up, down, down. So we're looking at these two, right? The reason why we have to consider all these together is because it is a conjugated system. So if we remove this pi bond right here, then we wouldn't even be doing this analysis. But compare it with this, uh-oh. Let me just take the orbitals out of those two and see what happens. In phase, in phase. I'm doing the way Wesley is showing me because that one answers the question correctly. What's wrong with this picture? No. So because of these two orbitals right there, that this is not the this cannot follow a concerted mechanism. Otherwise, they both have to be in phase with each other. So that right there, these two orbitals are why it's not a concerted mechanism. Because those are the two we're considering right here. We're considering this orbital with, well, we're considering this alkene with this alkene. We're not looking, so we do include all four in our analysis to get to this like up, up, down, down shading wise, but we're only reacting this pi bond with this pi bond. Does that make sense? So it's still in the pi 2 one, but it's like we're cutting out that section of the pi 2.
How did you know that
It could really be either one. It would be the same thing either way.
you were focusing on the pi bond? That make it possible to be a certain reaction.
Right, but it would still be the same thing either way. Let me think. I see what you're saying.
Because the whole premise of it not being concerted is that you have those two pi bonds out of phase, but there were four pi bonds, and one of the sets wasn't. So I think those two pi bonds.
Oh well. For one thing, because that's what the problem that's the bond the problem specifically identified. So like if we were this problem has like whoops. This problem has like 4 fluorines attached to it, something like that. And so by analyzing the products and the reactants, like doing a little bit of retrosynthesis, we just knew that we were working with that particular one, just because of the way things are pieced together. Does that make sense? Technically, yeah, it could add over to the other side, but for this specific pi orbital, no. So it'll say specifically on the test like what you're looking at, and it shouldn't be a particularly hard problem, but we did do a lot of work for that one problem. But just keep this in mind. If you just only write this on the test and say like, oh yeah, full points, like, no. What, this?
Yeah.
So it's because these two will not add up to each other. They'll create an anti-bond. These two will come together because they have the same sign. This is negative. Those will just basically just repel. Okay. I think. Diels-Alder.
Isn't that where you have like 4 carbons and then ethylene and it basically
It makes this.
Oh, okay. But so does that happen in one step?
Yes, that is concerted because the HOMO and the LUMO will add up together. Okay, we're 41 minutes and 33 seconds in. See right there. Yeah. Yeah, that's generally that is the case. There probably are some specific ones where it like doesn't happen like that, but yes. Okay. So I think we've done a pretty good job of carrying or of getting over aromaticity type of stuff as far as molecular orbital theory goes and the reaction stuff. For the reactions, they're all going to basically, let's see. Let's touch on the reactions of aromatic compounds really quickly, and then I really want to talk about this one, because this is a specific question. So pay attention, guys. Actually, what do I want to do? Let's do the kinetic versus thermodynamic first, and then if there are any reactions you want to go over, I know Jacob has one he wants to go over, so let's go over kinetic versus thermodynamic really quick, and then we'll get into some reactions. But this test is nice because all the reactions basically follow the same steps, except for SN1, SN2, E1, and E2, which are the aromatic reactions we've seen basically follow the same steps. So, hooray for you! Notice it's red again. So kinetic versus thermodynamic. So kinetics specifically refers to like how it happens. So like if we're analyzing the reaction mechanism, like how the atoms move back and forth, how the electrons leave, how the Levin groups come off, those are the kinetics. When we're looking at thermodynamics of the reaction, we're basically looking at the stability. Stability of molecule. So we have to be careful in this respect because really to compare, and I'll make this note too, high T, typically. I think that's right. If not right, then I'll give you points for it anyway. No, that's right. I'm pretty sure that's right. Low T. T equals temperature.
Might I just say, look at how neat that handwriting is.
So kinetics and thermodynamics are always in competition with each other. And so the specific conditions that you create for the reaction will influence what product you get more of. So the one that we've seen that specifically uses this, and this is again another problem from your recitation, not recitation, from your problem set. I don't remember which one it is. It's like 12 or something. It's pretty long. When you take this and do HCl, so to figure out which one will win at the end, we have to look at the intermediates or transition state, if there are no intermediates, and we have to look at the final product. So this reaction right here has potentially 2 intermediates. So first of all, we will take that proton, form the carbocation. Uh-oh, what's wrong there? Well, yeah. There's actually nothing wrong, I just want to see if you were paying attention. But this can actually resonate back and forth to make a secondary and a primary both allylic carbocations. However, this one is more stable, and this one is less stable simply because of the number of carbons it's attached to. Allylic means you have allylic basically means you have a double bond next to like a lone, like some empty orbital or filled orbital, and the double bond just goes back and forth between the carbons. So that's really all it means, because it's shifting. The positive charge here shifts between carbons 1 and carbon 3. Does that make sense? So because we get two different possible intermediates, that's when kinetics and thermodynamics hop in to save the day. So let's look at the more stable intermediate. This will lead to the kinetic product. So when we say kinetic, it basically means like the reaction, how it happens, and also how fast it happens, not just what happens. So let's do the kinetic route. Kinetic. I'll leave that one in green, and I'll do the thermodynamic in red, I guess. So we've got our energy going up. We've got our reaction progress over here. So we jump up, form the intermediate right there. Then we have a little hump right down here. Oh yeah, and we have the chloride in there still. The chlorine will hop onto that positive charge, and let me bring this down just a little bit, like that. It's not to scale. We make this, and now the thermodynamic product. Let's do that in red. So they both start at the same place, but the thermodynamic product is actually going to have a higher transition state. Oh wow, I didn't know I could do that. So they'll actually go up higher because it has the more unstable intermediate, the primary versus the secondary carbocation. And so looking at it like that, and so we have the chloride, and then, oh wow, why do I say that a lot? We're supposed to know. This will actually drop way down in energy to form the, wait. No, I'm missing a carbon. I drew it the wrong way. Like so. And so this one here was this is the 1,2 product, and this one here is the 1,4. Which one is more stable overall? No, that's not the question. You can see which one is more stable overall, but why is the thermodynamic product more stable? Yeah? Yeah. More substituted. And hence more stable. And this is only mono substituted. What? Mono means one. So depending on the conditions you have, you can either get the kinetic or the thermodynamic product. And so in the question, be careful to pay attention to what it says. So read the question very carefully. So that explains the difference between thermodynamic and kinetic. Oh, yeah, that was what was tripping me up. There we go. Back to pink. Just so you know, these files usually become like 20 megabytes. And with the recording, now it's at like 50 minutes. It's gonna might reach a whole gig. So I'll post on YouTube, but okay. So now let's hop into some reactions. Oh yeah, what's your question? Well, it's because of the resonance we have in the middle right here. Because we flip the double bond or the pi bond back and forth, we get a primary versus a secondary carbocation. You mean on each carbon? You mean if we go back this way? You mean like move it here? Well, yeah, but that just transforms it back into the other one. If we flip this one right back, if we flip this bond over here, yeah, you're right. We do get the secondary carbocation out of it, but it becomes the other intermediate. So, I guess technically yes. The thermodynamic, because it forms a disubstitute alkene, and the kinetic one, because it only forms a monosubstituted alkene. Well, the number of carbons that they're attached to. This one right here has 2 carbons surrounding it.
But in the transition state, there's going to be both.
Yeah.
It kind of depends on your temperature, which one you're going to have, right?
Basically,
Both
yeah.
at the same time.
Yeah, they're still resonating back and forth, but depending on where you're at, what temperature you have, it'll influence how much one.
The thermodynamic one, the one with the higher transition state, that's going to happen more at higher temperatures because it requires more temperature to get to that point, right?
Yeah, requires more energy.
So if you have a higher temperature for this reaction, there's going to be more of the thermodynamic product.
Yeah.
That's what it is.
Mm-hmm. Saul had a question.
I remember Dr. S mentioned something about the other one.
Yeah, so I'd say that the kinetic one is potentially reversible. And the other one, not so much, just because of the amount of energy we have to use to overcome the barrier. Well, if you have a ton of energy, yeah. But the kinetic one can go back and forth pretty easily too. Again, just pay attention to the conditions present in the problem. Yes, Kyle?
The thermodynamic product lower energy because of stereodynamics that CO
Yeah, that's one reason why. It's disubstituted. It's more hyperconjugated. Yeah, the alkene. That's why I wrote more substituted. Or I should write di. Yeah? I would just say for thermodynamic, whoops, I want to put that in red. I'd say the thermodynamic, let's just like ballpark range 150 degrees Celsius plus, and for kinetic, we'll just stay around room temperature. 25 to 50 degrees Celsius. Yeah, I'm not sure if those are the exact numbers, but that's relative. Okay, now let's get into on recording. You don't need to know. Okay, there's here. Well, I think we'll be fine with only 4 more minutes, and I can't charge it while it's plugged into this too. So Jacob had a specific. Notice how it's red. Red, 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 red. But this one he said specifically would be on the test too, so no guilt. So this one is combining adipic acid, which is this guy. Doesn't really matter how many carbons there are, plus the 6 carbon 1, 2, 3, 4, 5, 6, plus the 6 carbon amine group. And these hydrogens we can easily replace with R's. R just means like carbon group or of some sort. Again, this is where we take into account pKa values to determine which one is the nucleophile and which one's the electrophile. So ammonium has a pKa of about, I think it's 9. And carboxylic acid is 5. No, I don't think that's the ones are, but I do know that this one will be the nucleophile. This one over here, nucleophile. Electrophile. In the beginning, God created the heavens and the earth. He also created the carbonyl compound. He also created the carbonyl group. Nothing quite compares in its majesty or glory. Whenever you see a carbonyl compound, that's a basic dead giveaway that it's going to be an electrophile. So how's this going to work? Okay, well, first we'll take the lone pair of electrons on nitrogen. Yeah? Yeah? It's ammonium. pKa of ammonium, not of ammonia. So, first thing that's going to happen is we go, whee! Swing up on here, pop those electrons up, we get something like this, and I'm just going to abbreviate it because I don't want to keep writing it out. Oops. We've got O minus OH, and then NH2 plus. Wait, yeah, because we have that R group over there. And so what needs to happen over here is we've got to generate a good leaving group once again. Let's see. So for this one, this is a problem where we're actually going to need an acid to help us out, because if we just pop off this hydroxide, it's going to want to come right back on. So here I'll just say we'll add an acid right there. So we'll say this hydroxide right here picks up the H, this becomes A minus. Then this A minus, this base will pull off that hydrogen, one of those hydrogens off the nitrogen. So we get, in the next reaction, OH.
There should be an extra arrow going from the nitrogen hydrogen bond onto the nitrogen. I just didn't draw it in there.
OH. Then NH, R, and then OH again. But we have the acid that we regenerated. Lone pair of electrons on oxygen will be like, whee! Pick it up. Drop it off again. Now this is becoming a long problem. And then, aha, that becomes H2O plus. And now, NHR, It's acid catalyzed. It's adipic acid plus some amine compound. It's the last one we cover today. We've gone a couple minutes over, but that's okay. But then we can go, we reform the carbonyl, and we comes off the water. R. We get OH plus NHR. And then we'll just take another generic acid or conjugate base, take off the proton, and voila, we get the product VRC. Oh no, that's not an oxygen, that needs to be nitrogen. NH and R. And there we go. Yeah.
I'm not sure necessarily which reactions only occur in the presence of strong acids.
This one, it's basically the carbonyl compounds you have right here. The amide and the ester are going to require, well, basically the amide, the S, and the ester will both require a strong acid. The acyl halide L, E1 requires strong acid. Yeah, E1 requires strong acid. I think it's just basic. Okay. Before everyone goes, I just want to make, some of you came in late, but here are the 3 highlights of this week. Because one, on Sunday is my 24th birthday. Hooray! Next Friday on December 6th. I don't know exactly. I think it's 6 p.m. maybe. It's gonna be the Welsh Choir concert somewhere in the JFSB. There will be nice food there. And I'll post this Winnie the Pooh link later on. And also, please write your TA reviews, because the better the reviews are, the more money I make.
God bless you.
Welcome.
Okay, that is the review. I hope this helps you, and I sent out the PDF to the class. Take a look at the memes really quick, and good luck.